Our sun has been burning steadily for 4.5 billion years, and it has another 5 billion left in its reserves, 10 billion years total. But a star 100 times more massive than our sun, it only lives for 3 million years. Earth itself is 4.5 billion years old. That means a massive star was born, burned through its fuel, and exploded in a blinding flash before our solar system existed. Your instinct probably tells you that being bigger should mean lasting longer. A massive star holds drastically more fuel, so logically it should have a much longer timeline. Look at this simple animated comparison to see why that intuition is completely backward. A small candle on the left easily outlasts a massive bonfire on the right. The bonfire has far more wood, but it burns through everything it has in a fraction of the time, simply because it burns with overwhelming intensity. Stars operate under the exact same mechanics. In the cosmos, extreme physical scale and immense power guarantee an incredibly fast, violent end. This cross-section diagram shows the physical mechanics driving that rapid burn. An enormous amount of stellar mass creates a crushing gravity, represented by those inward-pointing arrows. All that weight presses down on the core, which drastically drives up the internal pressure and the temperature. That extreme heat triggers runaway nuclear fusion. The hotter the core gets, the faster the fusion reactions occur. The star is forced to burn through its colossal fuel reserves millions of times faster than a smaller star just to generate enough outward pressure to fight off its own gravity. When we plot this on an exponential chart, you can clearly see the drop-off. A tiny red dwarf on the left burns so slowly it will live for 10 trillion years. Our sun sits in the middle at 10 billion. But as you move to the right, a star pushing 100 solar masses plummets to a lifespan of just 3 million years. The sheer physical weight of a massive star acts as a biological fast-forward button on its own existence. To see what holding together that much mass actually looks like, we can look at this dense region of our own Milky Way. Sitting roughly 7,500 light-years from Earth is Eta Carinae. In galactic terms, it is right next door. If you were to replace our sun with Eta Carinae, it would extend past the orbit of Jupiter and swallow the inner planets whole. Its surface boils at 40,000 degrees, compared to our sun's 5,500. It is also visibly, measurably unstable. This image captures the Homunculus Nebula, expanding outward at over 600 kilometers per second. Those two giant lobes are the visible debris from a great eruption in 1843, where the star threw off huge amounts of material without actually exploding. Astronomers know Eta Carinae is actively building toward a final collapse. It is a live demonstration that maintaining extreme stellar mass is a temporary state. Deep inside, nuclear burning happens in nested layers. Different elements fuse at different depths simultaneously. Each stage gets drastically shorter. Hydrogen lasts millions of years. Helium takes hundreds of thousands. Carbon takes thousands. Oxygen takes months. Then comes silicon. It lasts exactly 1 day. A cosmic structure that took millions of years to build completes its final, desperate act in roughly 24 hours. That single day of silicon burning produces iron. Every fusion reaction prior to this released energy, fighting off the crush of gravity. But iron absorbs energy. The outward pressure holding the star together simply switches off. What happens next takes less than a second. The massive iron core, the mass of our sun compressed to the size of Earth, collapses inward until it's the size of a small city. The outer layers of the star plummet inward, hit that newly incompressible core, and violently bounce. What you see here in these intricate, glowing filaments is the physical aftermath, a massive shockwave that tears the star apart in a supernova. A million-year battle against the overwhelming weight of gravity is completely lost in a fraction of a second. When these giant stars die, they don't simply vanish. The explosion violently scatters everything the star ever forged outward across light-years of empty space. This makes their deaths directly relevant to you. The calcium inside your bones and the iron pumping through your blood were forged in the exact moments of a massive star's collapse. If we track the heaviest elements on this periodic table, like gold, we find they require even more extreme conditions to exist. They are built during the absolute violence of hypernovae, or the collision of dead neutron stars, and then seeded across the galaxy. Without massive stars burning incredibly hot and dying quickly, the universe would lack heavy elements entirely. The complex chemistry required to build rocky planets or biological life simply wouldn't exist. Looking at our own sun, we see a star sitting in a perfect cosmic sweet spot. It is massive enough to slowly forge elements, but small enough to burn in a completely stable state for 10 billion years. But physical models suggest the very first stars in the early universe were entirely different. They were massive, fast-burning titans that lived for perhaps only 10,000 years, serving strictly as explosive forges to seed an empty cosmos. Because our own star burns slowly, its long time frame gave a world like this one a chance to actually form. It allowed oceans to cool and gave biology billions of years to evolve into beings capable of looking up at the night sky. The biggest stars in the universe don't get to grow old. They burn incredibly violently, and they end quickly. But the universe required their brevity. They had to burn fast, so everything else could last.